Morning. Since we were so eager to graph this last one, I thought we would do it on a video. The equation is y is equal to negative x to the 4 x squared minus 4. This is an equation where the degree of the numerator is greater than the degree of the denominator. We have to use this method to graph it. We know that because there's not going to be any horizontal asymptote. We know that the vertical asymptote is going to be x that makes the denominator equal to 0. So, express this in a factored form. There are actually two vertical before, where we only have one. So we can say x is equal to 2 and x is equal to negative 2. And that also makes our domain just be x cannot be plus or minus 2. But that should match our vertical asymptote. Now I'm going to look at the unbehavior asymptote. EVAs come from dividing the numerator by the denominator whenever the numerator has a greater degree. Plus 0x minus 4, keeping our 0 terms in place. And then divide that by, we have to do negative x to the 4th plus 0x cubed plus 0x squared plus 0x plus 0. And then look at the terms. So we multiply by a negative x squared. We get negative x to the 4th plus 0x cubed plus 4x squared. Change the signs. So that becomes plus, minus, minus. And we have 0x cubed minus 4x squared plus 0x. Well, then we're just going to add a 0x. That doesn't change much, but it keeps things place marked. So 0x cubed plus 0x squared plus 0x. Don't really need to change the signs. But I bring down negative 4x to the 4th plus 0x plus 0. And my last step would just be then to multiply by negative 4. I'm going to be lazy and leave it there since I know the remainder is irrelevant. And this gives me an unbehavior asymptote of negative x squared minus 4. That's a parabola. That's different than what we've done as well. And if we want to graph that parabola, we can graph it through a few means. Probably the best means that we've done is to keep it simple to do transformation of base points. We know the base points for a parabola are 0, 1, 2, becoming 0, 1, and 4. And that will transform. This transformation has a stretch of negative 1 and a vertical shift of negative 4 without a horizontal shift. Keep in mind, this is only for the unbehavior asymptote. This is not for the entire equation itself. So don't get confused about stretches and vertical shifts. These remain for the x's, but the y's get multiplied. Sorry, stretch is negative 1. Y's get multiplied by negative 1. So negative 1 times 0. Negative 1 times 1 minus 4. And negative 4 times negative 1 minus 4. So those should be our base points for the unbehavior asymptote. Let's go ahead and graph it. I'm going to use a super big graph here because we have to go down to 2, negative 8. And we get, let's see, 0, negative 4, 1, negative 5, and 2, negative 8. And then the same points on the other side of our axis of symmetry. And that I'm going to graph as a dotted line because that's actually an asymptote. That is not it's not part of the graph. And then I might as well graph the other two asymptotes. We had vertical asymptotes at x equals 2 and x equals negative 2. So this is kind of the lattice work or the framework by which we're setting this graph up. Remember, there is no horizontal asymptote. So when I look at this, I see ultimately several regions that it could be graphed. I'm going to be careful to kind of expand this down here a little bit because I want to know that I want to see that this is actually a region that the graph could exist in. It could actually kind of be in this little pinch in between the parabola and the line itself. So we have to be careful about where it is. Okay, let's start with intercepts. This will kind of help us clarify this. If I take and pull down the original function itself, y is equal to under x to the 4th, over x plus 2 times x minus 2, my x-intercept should be 0. Because the only factor in the numerator is x to the 4th, and that's just x repeated 4 times. Since it's an x to the fourth, it's actually going to act like a double root and have a turning point and all that stuff. So my x-intercept is 0, which means my y-intercept is also 0, 0. If your x-intercept is 0, then your y-intercept has to be 0, because that's just the origin. So that's a point here. Well, if I kind of reason this out, then I know that it has to go like this for that part. We can now figure out if there are any points where it crosses the end behavior asymptote. Maybe down below it does. So I'm going to set negative x to the fourth over x squared minus 4 equal to the end behavior asymptote of negative x squared. Let's just be careful and watch our multiplying. We got negative x to the fourth is equal to negative x to the fourth minus 4 plus 4. Let's cancel. And then plus 16. So 0 is equal to 16, which is decidedly not true. So there's no point that it crosses the axis, which is the end behavior asymptote. So that part's done. Which means that if I go back to the graph, I actually have enough information to graph this now. If I look at, like, kind of from a left to right perspective, I know that it's going to have to be either in here or in here. The reason is because the domain is only x can't be 2 or negative 2. So there has to be some part of the graph to the left of that. And then it has to occur in either of those two regions, because we know it's not going to cross the end behavior asymptote. It's not going to cross this thing. Well, I'm going to reason that it has to be down in the blue area, because if it were up in the yellow area, we would see another x-intercept. And we don't see another x-intercept. So how do we sketch it all the way down here in this blue area? Well, we just do like a little small shape like that, keeping in mind that it has to approach both asymptotes. And then by symmetry, by the same reasons, we're going to have one over here, because we don't see another x-intercept on the right. And that's it. That is our graph. And if we look at the actual graph, it does match that.